please go ahead with your presentation. I'll try to be as little annoying as possible and just ask pertinent questions. Go ahead.
Okay, we are Group D, and I will introduce our challenge 2. Next page. So the task 1 is to investigating the pooling layers. Next page. So to evaluate how different pooling operation impact CNN performance, first we can see the first of all, our training data is fashion amnest, and it is the data set, and our model structure is simply the 2 convolution blocks. The first one is the convolution and plus ReLU and pooling layer, and this pooling layer will be replaced for maybe the max pooling, average pooling, and L2 pooling, and the second convolution layers. Okay, then that is the model structure. Next page. Okay, so for our pooling variants, we have max pooling, average pooling, and L2 pooling. And our optimizer use add-in and training for 30 epochs, and batch size is 64. And data split like 70% for training, 10% for validation, 20% for testing. Next page. Okay, then from this chart, we can see that our validation accuracy become like 0.92 at about 8 epochs, and after 8 epochs, their validation accuracy is almost the same, but like having some change over here. So, and we can see the validation loss. We can see that for the max pooling, the trend is quite similar to L2 pooling, but for average pooling, the loss decreased to its minimum at about 12 epochs. But for max pooling and L2 pooling, the minimum loss appear at about 8 epochs. So we can find out that the optimal early start point for the baseline model is 8 epochs, which maximizing the accuracy while minimizing the loss.
Nah, I'm not really, right? The validation, yeah, the validation accuracy. So here, this is this average over multiple seats? No, right? This is just one run, right?
Yeah.
So you see the problem, right? So you have to average this over multiple seats, otherwise, you're not sure about the conclusion that you have. Okay.
So I think like generally, how many seeds should I try?
You ask me.
Yeah.
How many seeds should you try? What would you do to choose the number of seeds?
I mean,
let me turn it back to you. How many? How would you decide?
I have to try 10 seeds and to average them, or
tell me what you would do and why you would do it. You tell me.
So I didn't try different seeds.
Okay, but how would you decide how many seeds you want to use for your averaging? What type of measure would you look at?
I think because different seeds make different like selection when having some random operation. So yeah, this may produce different results, but like overall, I don't think it will impact a lot.
I mean, it's a little bit, you have to see it this way, right? So here the goal of the figure is to understand the performance of the different pooling layers, right? So your objective is not to have the best network, right? The objective is to understand the effect of the pooling layer. And so when you have a result, you average it across multiple seats and you look at the You look at the variance of the results.
Oh, okay,
If the variance is very large, let's say if the variance is larger than 10% of your accuracy, right? Then of course, how can you say that you have a good result when? How can you say that you can have a good inference of the role of the pooling layers when the results vary so widely, right? So
yes.
you do 10, let's say you do 10 for seeds, and then you see is like, oh, what is the variance that I observe, right? How much of the how if I look at the average result, right? How much of this average result is captured in the 90% percentile? And then you start reasoning is like, for example, right? So if you notice, this is a first view of the performance of the pooling layers. So you do not know how the result or the conclusion that you have varies across different seeds.
Oh, okay.
The
I
pooling
see.
layer is good now, but in the other 9 runs, it's complete shit. I mean, it's complete garbage, right? So you're not seeing this aspect of the problem, correct?
Yes, yes. So I had to
It's like
try
you go to a
different seeds and
restaurant
see.
once. It's like, oh, this is the best restaurant in the world. Of course, you cannot say it, right? You have to go to you have to sample the restaurant multiple times and then take a decision based on that. What's the point of being the best restaurant in the world for one day a year, right? Go ahead.
Okay, okay. I will try different seed next. Yeah. Next page. So from my the specific seeds results, max and L2 pooling appear to have fast initial convergence and reach their optimal validation loss and accuracy at about 7 to 8 epochs than before overfitting. And for average pooling, they have slower convergence and delay the overfitting until 20 epochs. Okay, next page.
So you see here, like this, the discussion goes to this slide, right? You cannot tell me plus and minus a certain accuracy. Right? There is no reliability that you can attach to these statements, correct?
Yes, yes.
Go ahead. You got my point.
Next page. Okay, for the max pooling, because it just picked the maximum value for each pooling, so it will capture the most prominent feature in the local region. So it's very reasonable that why rapid convergence. And for average pooling, it have smooth context because it compute the average of each when the pooling happen, they compute the average, and so it will be smoother. So it explain why it's converge slower. And for L2, it compute the roots of sum of square. So, but in this case, it perform very similar to max pooling. So it's mainly because when computing the root of sum of square, the maximum value will affect the final value a lot instead of the smaller value. So it's very similar to max pooling, but still preserves some smoothness. Next page.
I mean, just to comment on that, go back one.
Okay.
Go back one. So you see this L2, right? 2 is the norm, correct?
Yes.
So what happens as P grows large then? As P grows large, what happens?
P goes large, it becomes smoother.
No, the opposite. As P goes larger, you go toward max pooling, right? And in fact,
Yeah.
L infinity is equal to max pooling, right?
Yeah, yeah.
Go ahead.
Okay.
Just giving context to your point. Go ahead.
Okay. So we have the third question. Does the pooling significantly impact accuracy? From our experiment, while the peak accuracy are comparable, but the training dynamics, I mean the convergence speed and overfitting onset are significantly impact. And for the second question, does average pooling lower accuracy? from my experiments, it doesn't strictly lower the absolute ceiling, but its smoothing effect require more epoch to learn to compared to others pooling methods. And the third question is, does L2 pooling improve generalization? In our experiment, L2 acts as a robust alternative to max pooling, but does not show a drastic improvement in generalization. Okay, next page.
Hello. Yes. Okay. So for task 2, this is where we essentially look at the activation functions and then next page, please. So here I also did like the same mistake as everyone else did, where I essentially only looked at like when they were strictly 0. And for this analysis, I used ReLU, LU, 10H, and Swish. Next page, please. So here, looking at the graphs, we can see that the ReLU performs the best, even though it has like a lot of like strictly dead neurons. And I think it's quite hard to say like how the dead neurons affect the performance, since we only have like the ReLU that actually like has dead neurons in our case. But yeah, and then we see like Swish and LU are slightly lower, and then 10H is the lowest. Next page.
Yeah, we discussed this last time, right? I should have said more clearly, like, or take a certain threshold for the 10 neurons, because of course, yeah, as you said, right? So some activation function don't go exactly to 0. Go ahead.
And yeah. And then here we can see like that the 10H is probably like so weak because looking at the average gradient norm per epoch, you can see that the gradients are very low. So it like learns very slowly compared to the other things, like the other algorithms. And then, but yeah, you can see that like just ReLU performs the best here with the validation loss and also validation accuracy, while LU and Swish are like somewhere in the middle, and then 10H is the worst. Next page, please.
Did you smooth this out across? This is smoothed out, right? How many average across how many seats?
I don't remember actually.
See, when you let Codex write all your code, then you forget.
I think it should be around 10.
Yeah, it looks like 10. Yeah.
Yeah, I think it should be around 10. And then last page, next page, please. Yeah, but essentially, I think because like when I was training the data and stuff and had the neurons plot, I was like, this looks really wrong. I was like, yeah. But I guess like based on what we see, the dead neurons don't really affect the accuracy. But at the same time, I know that like the dead neuron plot is very wrong in my case. So I would say like the conclusions that we can make from this is probably not that good. So maybe we should just like not make any conclusions. Yeah.
That's always a good thing in life, right? Not to make any conclusions.
Yeah. Yeah, that's it for me. Thank you.
Okay, it's me for text 3. Next page. Okay, according to previous text, ReLU and average pooling get the best performance. So in text 3, we use a fixed architecture, average pooling with ReLU activation function, with 10 rounds and 8 epochs per round on a fixed split. We also use a fixed seed list for all initialization strategy. Okay, next page. In our result, validation accuracy ranking is P is better than Saber than uniform. From the plot, the mean accuracies are approximately 0.917, 0.911, and 0.9. P initialization wins by about 10% advantage. As you can see, the results were close. In the other hand, dead neuron counts are relatively close across methods. The Saver has the lowest mean dead neurons.
followed by uniform, then heat initialization. Okay, next page.
Yeah, remember the discussion that we had last time, right? So this comes at a cost, and the cost is a complexity cost of generating these random variables, right? You remember the discussion from last time, right?
Yes.
Can you repeat the discussion from last time?
Not really.
See, because you don't follow my YouTube channel, you know that's why you. Go ahead.
Okay.
Okay.
The chart on the left illustrates the difference in weight distributions generated by the same initialization method using different random seeds, while the charts on the right display the difference in weight distributions between.
But this is a question. This is after how many epochs? You trained for how many epochs and over how many seeds?
8 epochs and 10 seeds.
8 epochs and 10 seeds. Let me observe this a second. Eh? Very nice. Very nice. Just a second. Eh? Sorted distance. So the first one is the sorted distance, right? So it's very close. And the other one, EMD. What is EMD? Expected. What is EMD?
I don't really remember. Let me check the code.
You cannot just copy and paste from Codex. Come on.
Because I did this about 2 weeks ago. I don't really know.
And you wipe your brain clean. You do things for 2 weeks and then you forget. What's the point of studying if you don't remember what you do after 2 weeks? Jeez.
Historian-based Earth movers distance.
Earth mover distance. Yeah. Do you look up what is the Earth mover distance?
It's a Earth mover distance.
Yeah, but do you look up how you compute the Earth mover distance?
How I compute?
Yeah, of course. What type? Because it's a distance, right? So what type of distance is it? Do you remember?
Where is it?
It's very beautiful, huh? It's a very beautiful mathematical thing. Across strategy. Sorted distance. Nice. It's nice.
Do I need to show you the code or what?
No, I mean just for you. I'm asking you because it's a mathematical concept, right? And I'm asking you if you looked into this mathematical concept. Like if you present something, right, but you don't know how it's calculated, what is the value of it, right? Like for example, you see that on the right hand side, right, you have many more outliers, right?
Yes.
So what is the difference? Like, is that a good thing? Is that a bad thing? Why do you have?
I think this shows which initialization is the closest.
Yeah, but that's the point, right? It's closer in this Earth mover distance, right? So
yes.
So if you don't understand how the distance is calculated, then it's kind of tricky to make sense of it, right?
No, I don't really understand.
Very good. Very good. Okay, go ahead.
So both heat and savers are scale initialization methods specifically designed to mitigate the vanishing or exploding gradient problems in deep learning. They dynamically adjust the variance of the distribution based strictly on the number of inputs or output neutrons. This mathematical constraints ensure that the shape of randomly generated weight distribution remains highly stable and consistent across different initializations. Without this specialized scaling, the pure uniform distribution yields randomly generated structures with noticeable poor stability. In a way, this diversity analysis, it shows that Saver versus he is the closest pair, getting lower between strategy distance.
Yeah, that's strange, right? That's strange because they are two completely different initialization, but they get a distance across these two initialization, which is lower than the distance with the same initialization, right? So it's a very strange result, right? I wonder what happened.
I think the logic behind Saver and he shares the same origin. Both center the weights around zero and apply a very small variance. Saver was.
I agree, but you see that the average that you have, it's the average that you have of the Xavier versus the he is lower than the variance intra he and intra Xavier, right? So it's very strange. You know what I mean?
Yes.
How can it be? It's very strange. I'm not saying that it's wrong, right? It's just you can think of it this way, right? So it's like think of it this way, right? So maybe you have two random variables, right? And the sum of the two random variables is what we are observing here, right? So you're telling me the variance of the sum of two different random variables is lower than the variance of the sum of two random variables from the same distribution. So it's kind of weird to observe. Now, I mean, that's just how the numbers are, right? No explanation. No better explanation. Because these are 8 seeds, right? You said 8 seeds, right?
10 seeds.
10 seeds and 8.
Yeah. Well, whatever. Okay, next page. Next page. Okay, thank you. Does initialization specifically impact final accuracy? Yes, initialization has a clear effect on final validation accuracy in these setups. Across 10 runs, the observed ranking is he better than Saver than uniform. In terms of robustness, the spread across runs appear moderate for all methods. No extreme instability, but uniform is less desirable because it is consistently lower in mean accuracy. He is the most reliable choice when the objective is highest final accuracy, while Saver remains competitive. And how does the distribution of dead neurons vary with the initialization schemes? Dead neurons counts differ by initialization, but the differences are not dramatic. The trend in this experiment indicates Saver has the lowest mean dead neuron count, followed by the uniform, then he. So initialization influences dead neurons distribution, but not in a way that perfectly matches accuracy. And do some runs convert to very different way configurations, yet achieve similar accuracy? Yes, the way the diversity analysis shows meaningful variation in learn parameter configurations between initialization strategies, while validation accuracy can still be similar. Okay.
Very good.
Next page.
Let's see. This is the fun part. Let's see who did this part.
I think I remember, but this part isn't here. So maybe I'll try to cover it for her, but
That's the best part. That's a nice part. Okay, let's see. The
yes, I'll
teams
just
last time they did this sign thing, this exploding sign. It was nice. Let's see what you guys did.
okay. So I'm just gonna present based on like the documents that
You're still
we
responsible.
got
You're
from
still
her.
responsible. Don't try to wash your hands of the hair. Go ahead.
So this task focuses on the design custom. Wait. This task focuses on designing custom activation and pooling functions, and the objective is not only to compare accuracy with standard methods, but also to evaluate effects on dead neurons, gradient stability, and training dynamics. Next page, please. So the custom activation function introduced here is called smooth PLU. It is constructed to behave linearly for large inputs while maintaining a smooth transition around zero. Unlike ReLU, which completely blocks gradients for negative inputs, smooth PLU ensures a strictly positive slope everywhere. This prevents neurons from becoming permanently inactive. The parameters alpha and beta are learnable, meaning that the network can adapt the activation shape during training. Next page, please.
Go back. Let me think a second. So you linearize that one there, plus you have x multiplied by a sigmoid, okay? And you have this beta parameter, and the beta controls the temperature. A change of convexity. And then what do you say there is differentiable almost everywhere? Where is it not differentiable? It's always differentiable, right? There is no singularity, right?
I have no clue.
Ah, you took analysis, right? In Goddamn high school, right? Where is the singularity of the function? There is no singularity.
Singularity function.
There is no discontinuity in the derivative, right?
I haven't looked that much into it. I'm just like showing, yeah.
I see you're washing your hands from your responsibilities as a team member. It's very bad.
Yeah, but
Is it convexity, right? There is a change in convexity. Yeah, it seems there's a change in convexity. Yeah, good. There's a change in convexity around 0. Nice. And then you take the derivative with respect to beta. So you also optimize over beta. So beta you also backprop through beta, right? So beta is like your correct? Okay.
yes.
So you have no bias though, right? Okay, but it should be okay. So you have no bias. Yeah, I would add a bias here, right? Because like in the ReLU, you can add a bias to the ReLU. That's the only thing that I will do. Okay, go ahead.
All right, next slide, please. So this is the custom pooling. So in addition to activation, 3 custom pooling strategies are introduced. Attention pooling assigns learned weights to each element in a pooling window, allowing the network to focus on the most relevant spatial features. The soft medium pooling provides a smoother and more robust alternative by emphasizing values near the local mean. And the energy weighted soft pool introduces a learnable parameter beta. When beta is small, the operation behaves like average pooling. And when beta increases, it becomes closer to max pooling. And this allows each layer to automatically learn its preferred balance between smoothing and the feature selection.
Very nice. Just a second. So here you see that you have a bias in the attention, right? In the attention pooling, you see that you have the bias beta C. Soft median is there, and then you do the soft median. Soft median. Okay, good. Go ahead. Go ahead. Soft median.
All right, next page.
Soft median. Why is it a soft? Can you go back? Sorry, can you go back one slide? How is that a soft median? Why is that a soft median? This soft median. Oh, what is this soft median? So you take the
Yeah.
I'm thinking why this you call this a soft median, right? Do you know? Do you know why you call it soft median?
Clue. It looks more like the
Yeah, go
mean
ahead.
kind of when I look at it, but
Yeah, exactly right. Because the median should be, you have to look at the amount of points on the left and the amount of points on the right and put it in the
yeah,
middle.
the middle, right?
So there is some
But here-
integration. Yeah, I'm a little bit confused why you call it soft median. Because then there is a 2D aspect, but the 2D shouldn't change. So if this one here is a good Gaussian approximation, right? Then I believe it, because what you do is that instead of doing the soft max, so if this is a good if the function is symmetric and Gaussian looking, then this should be a good approximation of the median, because you see that what you do is that you center the distribution around the mean, and then you divide it, right? So if you have a good approximation, the distribution is symmetric around the mean, that this will also coincide to the median. But I will not assume that the weights are symmetric and equally distributed around the mean, right? So soft, yeah, I will not call it a soft median. It's okay. Go ahead, but we agree. Yeah, go ahead.
Yes, next slide, please. Yeah, so here we look at the accuracy and the dead neurons. So the results show that the custom layers are competitive, but did not surpass the baseline. So the ReLU with max pool configuration achieves the highest test accuracy around 91.77%. The custom pooling methods combined with ReLU remain close within roughly 0.6 percentage points, and smooth PLU achieves slightly lower accuracy, around 90.5%. A more significant difference appears in the dead neurons. All configurations using ReLU exhibit dead neurons, especially in deeper layers. In contrast, smooth PLU and Swish reduce this to 0 across all layers. This
But again,
indicates that.
Yeah. Go ahead. Yeah, go ahead.
This indicates that the dead neurons are primarily determined by the activation function rather than the pooling method. But I guess this is like based on the previous wrong things that we had, right? So yeah.
Exactly. So if you had, let's say, if you decide the threshold and you look at the amount of neurons below the threshold, whatever. We got the idea. Okay, very good. Go ahead.
Next slide, please. So this is the training results and dynamics. The training curves highlight a trade-off. ReLU-based models converge quickly and reach lower loss values, but begin to show slight overfitting toward the final epochs.
Yeah.
Smooth activations such as smooth PLU and Swish produce more stable and monotonic validation curves, although they converge more slowly. Gradient norms further support this observation. ReLU maintains higher gradient magnitudes, which accelerates learning. Smooth activations maintain lower gradients, leading to more stable updates. The learned parameters also provide insights. Smooth PLUs data increases over time, sharpening the activation. For energy soft pools, the parameter beta remains close to 1 in earlier layers, indicating near average pooling increases significantly in deeper layers, indicating a shift toward more selective pooling.
So tell me again. So the bottom on the bottom figure, what's on the y-axis? It's not clear. What's on the y-axis?
I think it's a beta, right?
Yeah, just
Which-
because
which one do you-
that's what you say about the beta.
Yeah.
Because the beta is initialized uniform. Okay, it's still good. Okay. So because the left is the PLU parameter, right? So the PLU will be the beta, and the energy soft pool beta. Can you go back and we see what are the parameters of the PLU and the parameters of the soft energy? Can you go back? So the PLU should be the mixing, right? So should be the alpha, right? This 1 minus alpha time alpha. And the other one is should be the beta parameter, which is the. Can you guys go back? What's the energy of this energy pooling? Back. Go back. Here. Is the temperature. So the energy weighted stuff, the beta is the temperature, right? So it decides. So it's a soft plus, right? So beta has to be positive defined, right? You don't want it to change to a negative beta. And it controls the temperature of the exponential. And the alpha was in the mixing of the linear and the x times sigmoid term. Okay, go ahead.
All right, so next line. So the final interpretation of the results is that in terms of accuracy, the custom functions do not provide a consistent improvement. Performance is largely dominated by the choice of activation function, with rarely remaining the strongest baseline on this data set. However, in terms of stability, the improvements are clear. Smooth PLU eliminates dead neurons entirely, reduces gradient magnitude, and produces smoother training behavior. The pooling results also reveal an interpretable pattern. Early layers benefit from averaging, while deeper layers benefit from sharper feature selection. Overall, the baseline configuration remains the best choice for maximizing accuracy under limited computational costs. However, the custom methods provide advantages in robustness, interpretability, and training stability, which may become more important in larger or complex settings. I guess like while we say that like the other things don't have any dead neurons is kind of wrong, the final interpretation here, but yeah.
It's okay. Yeah, good. Okay, very nice. Let's see the last one, the CAN network. Let's see. Let's go tell him about the CAN network.
Yeah, so I'm going to present the final part of our project test 5, the simplified CAN model. First, I take our model setup and code architecture to make it the computation more efficient. I used an open source project called EfficientCon from GitHub. For our code,
in Python, it's gonna be super slow, right? So of course you have to take something already packaged. Go ahead.
yes. For our code architecture, we combined a CNN with CAN. We kept the best CNN blocks from our previous tasks, which include convolution layers, average pooling, and ReLU to extract image features. After the CNN part, we flattened the image into an array of 3,136 numbers. Then instead of using traditional fully connected layers, we passed this size input directly into a CON layer with 64 hidden nodes and 10 output classes. We trained this model for 10 epochs using the Atom optimizer. To strictly control the computational cost and follow the guideline, we limited the CON network depth to 2-layer with the shape 3,136 to 64 to 10. Furthermore, we kept the number of learnable kernels per connection to 5 by using the default grid size, ensuring problems remain tractable.
Of course, it's very heavy.
Now let's look at the learning curves. Our model achieved a training accuracy of 94.8% and a validation accuracy of 92.12%. This 92.12% is very comparable to our pure CNN baseline. Also, Because the gap between the training and validation line is small, it shows our model has good generalization and does not suffer from severe overfitting.
Very good, very good, very good. It's a tricky word. Go ahead. Okay, let's see. So these are the learn function, right?
Yes, as you can see in the chart, the curves are smooth and have clear shapes, which means they are high interpretability. interpretability. Also, the curves connecting to different hidden nodes have completely different shapes. This proves our network is learning a wide variety of distinct features.
Let me think. Let me think. So this one are the hidden nodes. Is this the final layer, right?
Yes.
So this is the function to hidden node 0 there, right? No, Nofal. Very good. Nofal is here. Nofal is here, guys. It's not following a lecture. It's... So let me just think a second, right? So you have the change sign, the activation function changes sign. And you have this strong negative response to... This is just one shot, right? And this is the one shot learned after you said 8 epochs, right? 8 epochs. So this achieves 92% accuracy, right?
Yes.
And this is two. So this is from the... So here you have the output layer 10. The middle one is 64, correct?
Yes.
So this is the one of the 64 ones. Let me think. I'm observing. Give me a second. So if I take the red and I flip... Oh, okay, good. It's around 0. I'll tell you something, okay? Then you tell me if it makes sense. I suspect, right, that hidden the activation to hidden node 3 and the activation to hidden node 1, they're sort of symmetric one to the other, right? So I was wondering, right, if this is a case of redundant neurons, because what we discussed before are the dead neurons, which is one problem, meaning that a neuron is unused. Another way in which a neurons could be unused is another way in which a neuron could be wasted if it's the neuron learn the same set of weight of another neuron. Agreed?
Yes.
So this is what I'm wondering, right? If we observe something like this, right, that the two neurons, they learn the same features, right? And then you understand that any linear combination of these two features will give you the same output to the downstream nodes, right? So that's what I was wondering.
Oh, yes.
Because those are the type of things that you always try to figure out, right? What are the redundancy that you have in the network? Especially because, let's say, if you then have to go and build this network, right? You would prefer to set to a node to be dead, so that then you don't have to implement it numerically, right? So you save computation, you save energy, you get more speed. So okay, go ahead. It's good. It's good. Go ahead.
Finally, we'll discuss our insights and the limitation of this model. What about the training time? Khan takes much longer. It took me about 44 minutes to train. I think it's maybe because Khan needs to calculate B spline curves on every single edge. Spline line. A spline curve on every single edge. The computational cost is much higher than standard CNNs. To make this problem tractable, we had to create a bottleneck, limiting the size to 3,136 and hidden nodes to 64 was absolutely necessary. However, our key insight is very positive. This experiment proves that placing activation functions on the edges work perfectly. It breaks the rules of fixed activations, allow the model to tailor custom nonlinear transformations for the idea. And that's our presentation.
Very good. Very good. Okay, nice. Nice. Okay, very good, guys. 2 minutes break. Go walk around, get some water, and then we go with the next group, and then we proceed. Okay? Ciao, guys. Walk around. Drink water. Hello, guys. Very good. Very good. So we still have one group, which is our beloved group E. Yeah. So group D had one member missing, right? One member missing. Group E, please get ready, right? One member missing. Didn't. Group E. Wait, go ahead. Go ahead. Is there a question?
No, I'm groupie.
Go ahead then. Go ahead then. Where is the excitement? Where is the excitement? Group E. Group E. Very good. So you use Canva. I see you have a nice. Very good. The graphic design is already on point, so I suspect I know. Yeah. Go ahead.
Okay, so we are group E and we have 4 members. So we split the text into 4 parts, which is polling, activation, initialization, and trying to design a better CNN. So let's go into part one. In this project, we've used the fashion MNIST dataset, and it consists of 28 times 28 grayscale images with 10 different clothing categories, such as t-shirts, shoes, and bags.
Do you
So
agree with these categories? Do you agree with these categories?
Or is it shoes? Shoes and no.
Like ankle boots. Do you agree that do you think the ankle boots should be a category? As an Italian that grew up with fashion, I don't consider ankle boots to be an item of fashion. Go ahead. What do you think?
Maybe it's not really fashion. Okay, so compared to the original MNIST dataset, fashion MNIST is more challenging and is commonly used for evaluating CNN performance. So part one, the goal is to build a baseline CNN and investigate how different pooling methods affect model performance. So we built a simple baseline CNN model. It consists of two convolution blocks, each including a convolution layer, a ReLU activation, and a pooling layer. After feature extraction, the output is flattened and passed through fully connected layers to produce predictions for 10 classes. So in this part, we keep all other settings fixed and focus on comparing different pooling methods. And in this experiment, we compare three different pooling methods. The first is max pooling, which selects the maximum value in each region and focuses on the most prominent features. The second is average pooling, which computes the mean and produces smoother feature maps. The third is global average pooling, which reduces each feature map to a single value, significantly reducing the number of parameters. All models are trained with the same settings to ensure fair comparison. And so now the figure shows a comparison of validation accuracy across different pooling methods. We can observe that max pooling generally achieves the highest accuracy. Average pooling performs slightly worse, possibly because it smooths out important features, and global average pooling can reduce overfitting in some cases, but it may also lose spatial information. So the figure on the right shows the accuracy curve during training, where the model gradually converges.
Spatial.
Yeah.
You understand? I was just.
Okay, so in conclusion, different pooling methods do affect model performance. Max pooling tends to preserve the most important local features and achieve the best result in this text. Average pooling produces smoother representation but may reduce discriminative power. These findings will be used as a foundation for later experiments such as activation function and weight initialization.
Very good.
Okay. This is my part. In this experiment, we compare different activation functions under the same CNN setting. We use fashion needs as a data set and keep the model architecture, optimizer, learning rate, batch size. The only variable we change is the activation function. And to make the comparison clearer, we can group the activation function into three categories. The first group is ReLU-based excavations, include ReLU, leaky ReLU, and the ELU. And the ReLU is used for our baseline. And the second group is smooth activations, including soft plus and switch. These two functions are smoother than ReLU, so we want to observe whether smoother gradients can improve training stability or accuracy. The third group is saturating activations, including tangent and sigmoid. These are traditional activation functions, but they may suffer from gradient saturation, especially when the input value becomes too large or too small.
Correct.
Okay, next page. Okay. First, let's answer the question, do fewer dead neurons lead to higher accuracy? From the validation accuracy plot on the left, we can see the several activation functions such as ALU, switch, leaky redo, and redo, all reach similar final validation accuracy around the low 90% range. However, from the dead neuron plot on the right, redo clearly shows a more severe dead neuron issue, especially in the fully connected layer, where the dead percentage is much higher than the others. And this-
50%. You guys have 50%. Wow.
yeah,
Because the other groups they had like 30%, 25%. You guys have 50% that you are. Wow.
Mm.
Okay, go ahead.
Okay, this tells us that having more dead neuron doesn't necessarily cause the model to fail completely, because ReLU still achieves completely accuracy. It matters, but they're only one factor among many. The overall optimization behavior and gradient flow are also very important. Okay, next page. Next. Oh, okay. Next, we look at the second question. Do smooth activation outperform redo on fashion? Means overall, the answer is
MNIST.
MNIST.
We agreed that this acronym, we will pronounce it MNIST. Just random. MNIST. Go ahead.
MNIST. Okay. Overall, the answer is slightly yes, but not a large margin. From the accuracy curves, smooth activation such as ELU and switch achieve validation accuracy that is slightly better than or very close to redo. Tangent also performs strongly in this experiment. These functions seem to provide more stable learning and avoid the severe dead neuron problem seen in redo. However, not all smooth activations perform equally well. So plus and sigmoid do not show the same advantage.
Sigmoid. I just
Sigmoid. I'm sorry for that.
There is no reason, right? I just joke.
Sigmoid. Okay. And in particular, soft plus trends more slowly and converges to a low accuracy, while sigmoid is limited by saturation and weaker gradient flow. So our finding is that some smooth activations, especially
Just a second, guys. Just a second. I lost just 1 second, guys.
Oh,
I lost my speaker.
In particular, soft plus trends more slowly and converges to a lower accuracy. Right. While sigmoid is
1 second, guys. Open volume mixer, open sound setting. Where is my Bluetooth? God damn it, where is my Bluetooth? J-Flip. Okay, I'm connected. Okay, should be connected. Let me check.
okay.
Okay, go ahead.
Okay.
Can you repeat? Sorry, I lost you. Yeah, I lost you a little bit. Go back 30 seconds. Press rewind. Go ahead.
So our finding is that some smooth activation, especially ALU and the switch, can outperform redo slightly, but the improvement is modest rather than dramatic. One likely reason is that smooth activations maintain non-zero gradients over a wider input range, which helps the model update parameters more consistently and reduces the risk of dead neurons. As a result, training can be more stable and less sensitive to unfavorable weight updates. Okay.
Okay.
Next page. To understand this more clearly, we can compare the training and validation curves of these activations. The rule learns quickly and reach strong performance, but it also shows the dead neuron issue in later analysis. Leaky rule behaves similar, but because it allows a small negative slope, it keeps gradient alive even when the input is negative. and this helps reduce dead neuron while maintaining good accuracy. ELU shows one of the best overall behaviors. Its training is smooth, its validation accuracy is high, and avoids the zero gradient problem more effectively than ReLU. This suggests that ELU provides a good balance between the optimization and the representation power. On the other hand, SOFLAT is different. Although it is smooth and avoids dead neuron, learning is slower and its final accuracy is lower. This shows an important trade-off. Fewer dead neurons do not automatically make better classification performance. Sometimes a smoother function improves the stability, but also weakens learning efficiency. Okay.
Oh, it's nice, right? Let me ask you a question.
Hmm.
Big question, okay? In all these curves, at the beginning of training, the validation accuracy is higher than the training accuracy. How do you explain that?
You say training higher than validation or validation?
Epoch 0, Epoch 0, Epoch 1. Validation is higher than accuracy. Validation is higher than train. How is it possible?
Oh, I think maybe because they belong to the same data set. So,
Right, go ahead.
so although we divide it into validation part and training part, it may be has the same influence on validation part. I don't really accurate and I don't know.
Exactly. Just be honest, right? You just don't know.
Yeah.
Because this is average, right? This is average after over 10 seats, right? This is 10 seats average, right?
Oh yes, yes.
So it's not a coincidence, right? Any idea? Any idea?
No.
I think it's just the weights in which it is calculated, right? Because when you do the training accuracy, you look at the original one, right? After one but the validation is after the update, I think, right? Probably they have already you know what I mean? You do a training, and then you update the model, and then you calculate validation. There is something.
Well, also like when it's just examiners, right?
Fashion.
Fashion. Sometimes just at the beginning of like during the trainings, when you randomly initialize the weights, they are performing better on the validation than they are in the training.
Of course. They
normal.
just random, right? But because it's a small data set. But you see, they also Epoch 2, right? I think it's just the scheduling in which the updates are made, right? I think you calculate the training accuracy, then you do one step of training, and then you calculate the validation accuracy. And so it's as if the validation accuracy should be shifted one to the right. Because you see that
yeah, make more sense.
because your initial step should be at 10%, right? So you should start with the accurate 10%. So if at 1 you already have 80%, it's because you already did one step of training. So I suspect that it's something like this, right? So I suspect that you should have shifted. You understand my point?
Yeah, I get.
Yeah, because otherwise it's too much. Okay, go ahead.
Okay, next page. Finally, just answer the third question: how do activation functions affect gradient and the training dynamics? The main difference comes from how each activation handles positive and negative inputs, and whether its gradient becomes very small. For tangent and the sigmoid, the output can saturate, which means the gradient becomes small when the input is too large or too small. This makes optimization harder and can slow down training. This is why sigmoid is particular tends to perform worse. For ReLU, the gradient is simple and efficient for positive inputs, which helps fast training. But when inputs stay negative, the gradient becomes exactly zero, and this can create dead neurons. This is main weakness of ReLU. And leaky review improves this by keeping small gradients on negative side. So overall activation functions affect chaining dynamics by controlling gradient flow. Functions with better gradient behavior such as leaky review, ALU, and switch usually chain more stably and avoid dead neuron better. From our experiment, ELU and switch appear to offer the best balance, while Redo remains a strong and efficient baseline despite its dead neuron issue. Okay.
Very good. As we discussed, right, that nuance is not always an issue, right? It's just something that occurs, right? But yeah, go ahead.
This is end of one part. Okay.
No, come on. I wanted to hear more about you. Go ahead.
Hi.
Hi.
Hello, everyone. Today,
Hello.
I will be presenting on task 3 of challenge 2. The focus of this task is to investigate how different weight initialization strategies affect the optimization process, final accuracy, and the diversity of learned representations in our convolutional neural networks. Okay.
Good.
Next page, please. To ensure a fair comparison, we keep the pooling layer and the activation functions fixed. We then independently, next page. 上页，不好意思。
Don't mess this up. This is your time to shine.
Okay,
Don't mess this up.
to ensure a fair comparison, we kept the pooling layers and activation functions fixed.
Okay.
We then independently trained the network multiple times using different random seeds for the severe heat and uniform initialization strategies to observe their mean performance and variance. Okay. Next page, please. To implement the different initialization strategies, we utilize PyTorch building nm.init module. We created a custom function that checks if a layer is a convolutional or linear layer. Based on the experiment's current strategy, it dynamically applies severe heat, which is called timing in PyTorch or the custom uniform initialization. We then elegantly apply this to the entire network using the model.apply method before each training run. Okay,
Finally, I see some code. Finally, I see some code, Well, not exciting, just some code about the weight initialization. So
okay.
I said because my student came to see the code, but it's not exciting code, but it's code. Go ahead.
Next page.
It's very important. Yeah.
Counting dead neurons was the most challenging coding part. You can't just look at the weight to see if a neuron is dead. You have to see if it ever activates. To do this without breaking the model architecture, we use PyTorch over hooks. We register a hook to every value layer. During the validation phase, this hook quietly intercepts the output activations, records the maximum value each neuron produces. And if a neuron's maximum output across all validation batches is still 0, we successfully count it as dead.
Very good.
Okay, next page. So finally, to calculate the distance between learned weights from different rounds, we face the permutation symmetry problem.
Correct.
Neural networks can shuffle their internal nodes and still be exactly the same. Therefore, an element-by-element comparison is mathematically invalid. To solve this, we extracted all the weights, flattened them into a 1D tensor, and sorted them. We then compute the average absolute difference between these sorted arrays to accurately quantify the distance and diversity of our models' optimization landscapes.
Question. Can I ask you a question? Can I ask you a question?
Okay.
So you understand the permutation invariance, okay?
Okay.
But there is also a scale invariance, right? So if you take all the weights, right, and you
Yes.
multiply them by 10,
Yes.
then you take the output weights and you all divide them by 10,
Yes.
then this is also another type of invariant, right? Because the network because the network output will be the same. Do we agree?
Yes. Okay.
How would you deal with this invariant? How would you do it? You don't need to rush. You can take a couple of seconds and to think about it. How would you deal with this invariance?
To,
You don't want this, you don't.
I don't know. Sorry.
Of course, there is. I mean, go ahead. Take your time.
Okay. So next page. First, let's look at the accuracy. As you can see, the model achieved around 92% accuracy across all three strategies, indicating that initialization doesn't significantly impact the final performance on this task. However, severe initialization demonstrated the highest robustness. It not only had the highest mean accuracy, but also the lowest variance, meaning it converges most consistently across different redundancies.
Very good.
Okay,
Very good.
next page. We analyze the dead neuron phenomena, which is common with radio activations. We found a very interesting result. Uniform initialization resulted in an exceptionally low dead neuron rate of only 0.5%. This is likely because restricting the weights to a very small uniform range prevents extreme negative values in the initial layers. In contrast, the long tail
I understand what you're saying.
effects
Because then if you have all negative layers, then the neuron is dead. So it never starts up. Okay, go ahead.
Okay. Uniform range prevents extreme negative values in the initial layers. In contrast, the long tail effects of sampling from a normal distribution, like in Xavier and He, increases the risk and randomness of neurons falling into the negative region of value and dying. So next page, please. Finally, we quantified the distance between different training runs by calculating the average absolute difference of the sorted weights. The data shows that key initialization, in particular, resulted in the noticeably larger weight distance between runs. This highlights a crucial concept in deep learning. Even though these models achieve similar accuracies, they actually converge to entirely different locations in the parameter space. Okay, next page.
Let me think about this. Jeez. Go back one slide. There is no rush. Okay, repeat this. But yeah, elaborate a little bit more. Yeah, go ahead.
Go back.
You went too fast. Yeah. Repeat this.
Even though these models achieve similar accuracies, they actually converge to entirely different locations in the parameter space.
Yes. But how can you be sure from this, right? How can you be sure? Like, you know what I mean? Is the 1%, is the 0.001% absolute difference a lot or little, right? Because this is absolute, this is not relative, right? So you understand what I mean? There's, it would have been nice to see some statistics about this, right?
Oh.
You understand what I mean? Because you say, very different, but can you really be sure that they're very different? Right? You understand my point? Go ahead.
Okay. So next page.
No. Go ahead. Explain to me your understanding of this. Go ahead.
Because
trying to rush to finish. You don't want to talk to me, yeah? Gosh, go ahead.
Because we insert the dead neuron percentage distribution. Wait a second. Didn't figure it out.
Okay, go ahead. Go ahead. Go ahead.
Okay, sorry. Next page.
I ask you questions and you. Yeah. Go ahead.
下一页. So in conclusion, while the initialization strategy might not dictate the final success of this specific task, it profoundly affects the learning trajectory, feature diversity, and the internal health of the neurons. This also provides an excellent baseline for our upcoming experiments with custom activation and pooling function in text form. Thank you.
Okay, another set of guys with the sign, but the sign now it's both in the positive and the negative domain, right? Okay, tell me about this. So you have the sign both forward and backward. You have this perturbation around the origin. Yeah, go ahead, guys. Who's gonna talk to me?
Okay, so in this part, we design a custom activation function, which is the below. And the main idea is to combine the two effects. The first term, the term with x, which gives the function a smooth gating behavior, which makes help the model learn more stable. In the second term, which is the term with sign, adds a small periodic component, so the activation function becomes slightly more flexible and more nonlinear. From the accuracy curve, which is the graph in the left, we can see that the training accuracy keeps increasing until the last epoch, which is the blue line.
Question. So
However,
you don't have a bias
yeah.
or anything here? You don't have a bias or a scaling term? Just straight up? There is no learnable parameter here in the activation
Okay.
function? So there is no bias or scaling? There is no learnable parameter in this activation function that you pick?
Let me check my code real
Let you
fast.
check the code. You understand my question, right? Because
Yeah.
usually you have a bias or a scaling term. Because otherwise the other layers in the network, you have to sort of account for this, right? It's not a big deal. Just wondering.
I don't think that there is a parameter.
Okay. Yeah,
There's just input.
Go ahead.
Okay, and
So because you understand my question, right? Because if you remove the parameters, then it's as if you, because you use this on the fully connected layer, right? On the 60 in the last layer, right? In the fully connected layer, you use it, right? So in my mind, I was just counting how many fewer parameters you have in your network since you don't have a bias here. Because if you had the ReLU, right, then you will have the bias on the ReLU.
Yeah.
So you will have, let's say, 3,000 more parameters. And your whole network, let's say, is maybe 6,000, 8,000 parameters. So in my mind, I was like, okay, so we achieved this accuracy, but we've let's say, maybe 20% less parameters. So in my mind, I was doing the accounting is the accuracy good or bad, right? Because here we don't know. Yeah. You understand my point, right?
Yeah. Yeah.
Go ahead.
Okay, so however, the validation accuracy starts to slow down after around 4 or 5 epoch.
And you see that the network is still learning after 10, right? So the network, since you have this sign, right? The network doesn't settle very easily around a zero, right? So because, for example, if you remove the sign, right? If you remove the sign, then the gradient will be around 0 when your x is equal to 0, right? But here,
Yes.
wherever you are, right, there is always a certain amount of gradient left. So that's why the network never really settles. It seems it keeps moving the gradient, right? It keeps learning, but the validation accuracy is flat already. Nice. Okay, go ahead.
Okay. Also from the loss curve, which is the right graph, the training loss keeps decreasing, but the valid loss becomes almost flat layer in the 8 to 10 epoch.
That's what I just said, right? Yeah. Go ahead.
Yeah. This means that the model is still learning the training data, but improvement or unseen data is limited.
You see my point, right? Because so your network is always searching, because since you have this sign term, so it never goes to 0, right? Because
Yes,
whenever
it
the
just
gradient,
go flat.
yeah. So the network is still moving around, so it's still learning stuff, but nobody knows what the network is learning, right? So it's good.
Yes.
Go ahead. Nice.
So overall, this custom activation is an interesting design, but in our experiment, it did not outperform the baseline. Its validation accuracy and test accuracy was slightly lower, and the training time was also a bit longer. So therefore, for this case, leakage ReLU is still better and more stable choice. Next page. Next, we compared 3 custom polling methods, which are hyper polling, software weight polling, and random polling. From the table, hyper polling achieved the best results, though
So,
you can see.
So what is hybrid pooling? What is the formula of hybrid pooling?
I didn't show in this.
Do you have it somewhere?
Because
the
I didn't
soft-weighted
show it
pooling,
on the.
right? Go ahead.
Yeah.
So the random pooling is clear. The soft-weighted pooling we saw in some other presentation, but this hybrid pooling, I mean, it's hybrid between what and what?
I didn't show in this PPT, I think.
See if you have it in the code somewhere, or if you have a page where you can see it. And because it's hybrid between, that's the thing.
Yeah, I think I need to change my PPT later after the presentation.
Okay, you don't want to do it live. Okay, I accept it. Okay, go ahead. You understand my question, right? I just don't know hybrid between what and what. Go ahead.
Yeah, I'm sorry about that. So you can see the difference between the 3 custom polling by the chart below, but you can see the difference between the numbers, which from the table, hyperpolling achieved the best results. It has the highest validation accuracy and also the highest test accuracy, which is around 0.9126.
Question.
Yeah.
So I thought that the hybrid was hybrid between soft-weighted and random. But if that's were the case, then it cannot have the lowest computation time, because the computation time should be the sum of the 2 computation time between the soft and the random, correct?
Yes.
So I don't know what hybrid means now. Now I don't know. Now what I thought meant hybrid, now I don't know what it means.
Let me check.
If you know what hybrid means, please, even in words, let me know. Otherwise, I'm very confused.
So the hyperpooling in my code is to make an average between the max pooling and the average pooling.
I see. And what is the coefficient of the average? Something that you just learn? Is it a learnable parameter, or is it just fixed?
I think it's just combine of two, like the two ways, which are
Yeah, but the combined with a coefficient or just combined with a fixed ratio? You know what I mean? Can you learn the parameter of the combination or not?
oh yeah.
Okay. Okay, makes a little bit more sense now.
So
Okay.
it will keep the strongest feature. So
Okay.
you can see that you have the better accuracy, but you have those lower training time.
Okay. Good.
I think
Good.
is why it looks like so not make sense.
Yeah, exactly right. Exactly. Now it makes more sense. Okay, go ahead.
Okay, and the soft weighted polling was slightly lower, and the random polling had the lowest performance among the three custom polling method. This results shows that the simply adding randomness does not always improve the model. Hybrid polling works better because it combines the different polling ideas which I have mentioned like 10 seconds before, and it can keep useful features while still reducing the feature map size. So compared with only one polling strategy, hyper polling keeps a better balance between performance and stability. In conclusion, among our three custom polling methods, hybrid polling is the most efficient one. Okay, next page.
Okay. Now the can. Oh, so the kernel for the can that you take, it's a tonnage and a sign. Okay. Okay, go ahead. Go ahead.
So at the last, we implement a simplified can inspired layer, which
Yes,
is
kernels.
showed
Go
below.
ahead.
Yeah. The purpose of this layer is to make the fully connected part more expressive. Instead of only using one simple linear transformation, we add a non-linear function to help the model learn more complex patterns. From the results table, simplify can CNN slightly outperform the baseline. The baseline accuracy was 0.9180, while the can CNN reached 0.9189. The improvement is not very large, but it still shows that this layer can bring some benefits.
Yeah, I
The
just
training time,
on this, right? Because the true cans they have more kernels. So you saw the other group, right? So you have to use a custom implementation. You have to download it from GitHub. I mean, this is not really a can in the sense that you only have two kernels, right? So it's not really. Yeah, you understand that the other groups they have different splines, right? So you can
yes.
really see how the composition is done. So it's suboptimal. Go ahead.
The training time is only increased a little from about 90 seconds to 92 seconds, so the extra cost is acceptable. Next page. Okay, from the training curves, we can also see that the training accuracy keeps increasing and the training loss keeps decreasing. However, the validation curve have some small it how do I say that word? It jumps. It has small jumps. And this means that the cane-inspired layer has stronger learning ability. But this generalized is not completely stable because it jumps small. Overall, the simplified can-inspired layer gives the best results in this part, but the improvement was small. So it may be useful, but it still need more experiments to prove whether it's consistently better, because it just got a small difference. I think it's 0.0009 difference in the accuracy.
But so this is why I push back, right? Because the idea of the can is that once your network is trained, you can look at the activation functions, then you can understand what type of functions are learned, right? So the idea is that you will have to go back and plot the different kernels and see if the kernels make sense, right? But
yes.
So the point is not to improve accuracy per se, but it's to improve interpretability. Anyway, go ahead.
Okay, and to summarize, we tried 3 different modifications in this experiment. First, the custom activation function added more nonlinearity, but it did not improve the final performance. It also showed mid overfitting, so leakage ReLU was still better choice. And second, among the 3 custom polling method, hybrid polling performed the best. It achieved the highest validation and test accuracy, which shows that the combining polling strategies can be useful. A third, the simplified can inspire layers slightly improve the task accuracy compared with the baseline. Although the improvement was very small, the additional training time was also limited. So overall, the most useful modification in the 3 experiments were hyper polling and the simplified can inspire layer. The custom activation was creative, but it was not better than the original baseline in the task. And this is our presentation.
Okay, very good, very good. Okay, good. Thank you, guys. Okay. Is there hands up? Go ahead with the hands up.
Professor, I want to elaborate the optimization landscape and the relationship between the similar accuracy and the large weight distance.
Okay, go ahead.
Despite achieving the same 92 accuracy, the model converge to a completely different weight configurations.
Yeah.
A larger weight distance proves they are not memorizing the same parameters. If the model only memorizes one specific answer, the weight distance will be exactly 0.
Yeah, okay. But this distance is pairwise, right? So
Yes.
you should look at the pairwise distances and have the distribution of the pairwise distances across different seeds and see the difference there, right? Because imagine that however your initialization is, you will learn one of 2 networks, okay?
Yes.
And there is a distance between these 2 networks, which is 10, right?
Yes.
Then half of your seeds will have distance 0, and the other half of your seeds are going to have distance 10, and then the average between the 2 is going to be 5, correct?
Yes.
So that's it, right? So if you just give me the average across all different seeds, I will see 5. But this does not tell me that that I haven't collapsed to 2 of the possible networks, correct?
Okay.
Good. Okay, well, what is the other thing that you want to clarify?
No, thank you, Professor.
Okay. Yeah. Also, that's why the other group, they have the earth mover distance, right? Let me just show you the earth mover distance because there was a good idea, right? Of course, it comes from generative AI, and students just copy stuff back and forth. But what can I say? It's your responsibility to learn. I'll do my best. So the earth mover distance, right, is maybe there is. Let me see if there is a nicer plot. It's I think what is a good example? Something like this, right? So the earth mover distance. Let's see if I click here, is it going to be a mess? Let me just check. No, not too good. Okay, it's good. So yeah, let's just let me just see if there is. This is the clearest one that we're going to have for now, guys. Okay. Let me just. I can do this. So at least it's big. So then I can share this. I can share this. At least we can share this. Okay, good. So the idea of the earth mover distance is this, right? So let's say that you want to go from this distribution to this distribution, right? So in the earth mover distance, you imagine that you pay a price of moving a certain amount of distribution from one point to the next, right? So you see here that the first tracks, right? You're just moving the weight around, right? Until you fill in this one here. So the earth mover distance compute the difference between this distribution in terms of this moving of weights, okay? So you pay for moving a weight of a larger distance, and you pay more weight. You pay more price as you move larger weights to longer distances. Okay, so this is telling you that the way in which you should compute the distance between two distributions, right, is by doing this operation. But again, this is a better idea of distance between distributions, so that obviates the fact that distribution can vary only by small weights between one and the other. But it does not solve the problem of this idea that you could have a certain number of attractor networks, right? So you will call them attractor networks. So when you pick a seed, the seeds will all be attracted to one of two or more possible solutions. Okay, so you can do this test by yourself. If you start with MNIST, almost wherever you initialize MNIST, you will collapse with just one network, because MNIST, it's a very simple problem and a very simple network, so it's easy to collapse in one solution. But if you go to fashion MNIST, I do not know how many solutions you will collapse to. My suspicion is that it will be, maybe 10, 15 different attractor networks. But the difficult thing is to account for the invariance of the weights, of the permutation invariance of the weights, and the scale invariance of the weights. So this is the point that I was trying to make with that part of the challenge. Okay. Okay, very good. So let's do this. We take a 2 minutes break, 3 minutes break, and then we do a little bit of NLP. We start doing language modeling in NLP. Then we have the movie review, and I'll let you guys go. Okay? 2 minutes break. Go get some water, walk around, stay healthy. Ciao, guys. Okay, guys, we are all nice and ready. So as I said, let's do a little bit of NLP, because the next topic is going to be natural language processing, which is in the last years that has been the topic, has been the machine learning topic which has most impacted the public opinion, right? So let's start discussing what is a language model. So outline here. So remember that we finish RNN, LSTM, GRUs, right? So when discussing language, we will see this sort of sequential view of NLP, and then we move on to some new architectures, which are transformers. Okay, let's go this. So the topic is very, very large. So this is an introductory bachelor course, so it doesn't make sense. But of course, the fact that machine learning model can use human language, it's something that one needs to consider very carefully and observe. Be very mindful about. But of course, this is your learning journey, so you are on this journey, even with or without me. So one first approach is to model languages as a sequential data. Okay, so what we conceptually imagine is that we observe a sentence of T characters. Okay, let's just imagine that all sentences contain T characters. If a certain sentence has less than T characters, then we will just put empty characters, and if it's shorter, if it's longer, we just cut it. So we have T tokens, T entities of language, 3 instances of language, and we imagine that this is generating as the product of a set of conditional distributions. So notice here that the product goes from T equal to 1 to big T. Okay, and this is a product of conditional distribution, and they go it is the distribution of x of t given x of t minus 1 to all the way to x1, which means right that we imagine that we start from the first word, then the probability of the first word is multiplied by the second word given the first word, which is then multiplied by the probability of the third word given the second word and the first word, and so on and so on and so on. Okay? So the idea is that when you observe a sentence, this is the application of conditional probabilities, right? Where we multiply the probability of the current word given all the past words. Okay, very good. And one can see this as a sequence of weather, right? As we saw it. As we discussed it last week, right? So the idea, the first day you see rain, then when you're predicting the weather for this day number 2, then you will say that the probability of the weather day number 2 is conditioned on the probability of the weather 1. So let's say in the case you will have the conditional probability of the second day given the first one. You will sample from this probability. And then when you go to day 3, the probability of the weather day 3 will be the probability, conditional probability of day 3 given day 2 and day 1. Okay, this is how you imagine. Okay, so in this case, the probability of rain given the cloud given rain given sun given cloud given rain. Right, so you see that this encodes our understanding of memory in the weather patterns. Okay. Why is it useful to accurately estimate the joint distribution of any given sequence of length n? The idea is that you don't want to lose information. Okay, so the idea is that the system processes a certain amount of memory, and you want to exploit the memory in order to have better prediction. Okay, so the sequential probability will be more powerful in general than trying to just predict the joint probability of the weather altogether. Okay, so in the reminder, we will focus on natural language, and this is because it's easy to interpret. It has a real world impact, and we can build models over this sequence, over this particular temporal sequence, which we can evaluate with our own human understanding of language. Good. So a language model represents how the language is used by a certain set of entities. Okay, so different languages arise from different people, for different gender, or for particular classes of text. And a language model represents how the language is used by a given entity for a certain task. One of the first uses of language model that was defined in the literature famously was the spam filter for Google, which is still working today. So maybe it's one of the most used machine learning models since the beginning of time. And basically, the language model looks at the emails that you have received and has to define whether the email was a spam or non-spam. So, of course, another use of the language model is to determine what is the language of a certain text, right? So when you use Google Translate can automatically detect the language that is being used. And the role of a language model is to estimate the probability of any sequence of words, okay? So let's say that we have the sentence, Eleni was late for class. And when we put this into a language model, we would like the language model to estimate for us what is the probability of this sentence. Okay, now this is something that you have to think deeply about, right? Because you have to imagine that the probability of this sentence lives in a very large space, which is the space of all possible sentences that one can produce in English, say, that have some logical sense of that could be used by human beings. Okay, so the idea of being able to estimate the probability of a certain utterance, it's a little bit crazy, right? Because there are so many different possible uses of the English language that imagine a distribution over this object, it is kind of baffling, right? But this is indeed what, for example, LLMs do, right? So LLMs are able to look at a certain amount of text and see what is the distribution, from which distribution they should sample to produce new language. Okay. So to imagine this, do the following exercise, which is to put in a partial text in Google, and this is, of course, this is a game that people used to do maybe 10 years ago already, right? So the idea is that when you put a certain entry in Google search, Google will rank the possible sentences that you're trying to write from the most likely to the least likely. So in this case, the person wrote, "How do I?" Right? And you see that most people that write "How do I?" into a Google text search, they are trying to write a check, to fill in unemployment, to download the Zoom app. So this screenshot really was taken during COVID times. And so this is the language model at work. I mean, the language model produces a sample, right? Produces a probability distribution of all the possible sentences that can be generated by a partial amount of text, and then they are ranked from the most probable to the least probable. Another one is the predictive keyboards that you have on your phone, of course. And then this is also the translation, okay? So translation is another use of a possible language model. Fake news versus real news, of course, another model that we are familiar with. So when we generate text, we can mention about autocomplete, speech to task, question answering, machine translation, and then classifying text. You can find authorship, detect spam versus non-spam, find which language it was, and so on and so forth. Language model are of our concern because we want to understand different NLP tasks that we'll be discussing in this course. But remember that when we model a certain sequence, you can expand the use of these tools to any sort of sequence, right? Not only to language sequences. Okay, so historically, how did people produce language models? Usually, people will start with n-gram models, okay? So the n-gram models are models in which you predict sentences from the context. And the simplest approach is the one in which you ignore the context and you just look at the probability of a word as if it were independent from all the others. Okay, so if you do that, then you can see that the probability of a word it's simply proportional to the number of currencies that we have in the corpus. Okay, so let's say that we look at this sentence again. This Eleni was late for class. We just go to our corpora of all possible English text that Gini has given us, and we look at the probability of Eleni, the probability of was, the probability of late, the probability of for, and probability of class, and we say that the probability of this sentence is simply the product of the probability of each single word. Okay, so in this approach, we disregard the joint distribution curve fully. We disregard, how the memory exists in the sequence, and we just take the product of this. Now, these numbers are somewhat realistic, right? Meaning that the probabilities here are on the order of 10 to the minus 3, 4, maybe. Yeah, this is the type of probability that we're dealing with, so that the probability of a sentence of 5 words will be this probability to 10 to the minus 4 to the minus 3 multiplied by 5. So the fact that a sentence has a probability of 10 to the minus 13 is not something surprising. And indeed, as we're discussing, right, since the corpora of all possible uses of the English language is so large, you can imagine that the probability of a single entry decreases very, very quickly. Decreases exponentially quickly with the length of the sequence. Okay, so this model doesn't have any logic, doesn't embed any semantics, and in particular the probability remains the same however we permute the sentence. Okay, so if we permute the sentence to class was late for Eleni, then this will have the same probability in this model. But of course, we do understand that this new utterance, this permuted utterance, has a probability which is much, much lower, right? And also, it doesn't give us any power when generating sequence, because if somebody gives us the partial sentence, and the sentence was like, Eleni was late for class, right? And we ask what is the next word, the model will always sample words from the absolute probability in the English language, right? So the most probable word in the English language is the, right? So whenever we want to generate text, our language model will always spit out the as the next sentence. Okay, so whatever is the model type of sentence that we're trying to generate, then the model will just keep generating the with little variation, right? Because the maybe constitutes something like 10% of the English text, right, or 15% of the English text. So when we sample, all other words will have a very low probability, and the will be the only one that is being sampled. Okay, good. Then this was not a good idea. So from what we can do next is to add the memory of one term. Okay, so now when we look at the relative distribution, we look at the conditional distribution of the word given the previous word that we used. Okay, so here when we want to look at the language model, we will have a window of 2 words, and we will produce the second word given the first word. So we start with the probability of Eleni, then we have the probability of was given Eleni, then the probability of late given was, the probability of for given late, the probability of class given for. Okay, so of course now we have the problem of estimating these conditional probabilities, but that's okay, right? Because, for example, to obtain the conditional probability of class given for, we will look at the probability, the number of times for class appears in the English corpora, and we will divide by the probability of 4. This is Bayes' rule. We know to use it since our high school, and this is how we will obtain these terms. Okay, so what is the issue here? So one issue that we observe is that there are the out-of-vocabulary words, right? So if we have a word which appears, we have, so you understand now that we are counting how many times, sorry, we are counting here how many times 4 class appear together. So imagine that there are 2 words that they never appear together, right? Two words when one never follows the other. If we have a bag of, let's say, k words, then we have a k-square such words. So we have a polynomially larger number of sequences that we're looking for. And so now it is very much possible that even if a single word appears many times, maybe never appear followed by another specific word that we can pick. And so this will make the probability estimate to be equal to 0. And so the language model will not know what to do when encountering this two utterances in one after the other. So this is an out of vocabulary sequence. Another one is that when we try to scale the memory of the process from 1 to 2 to 3 to maybe a few hundred, then we encounter the issue that we have a very large possible content of the memory. Okay, so if you think about all the possible sequences of four words in the English language, there are polynomial many of those, but only a very small portion actually occurs in the corpora. Okay. And this is a very large issue because when the language model has to be used, it has to be instantiated somewhere. So if you have this very large memory but is mostly unused, then we are not doing an efficient use of our resources, right? Because we have to store a matrix which is mostly containing 0, and so we are wasting our memory computational resources doing this. And so this prevents us from being able to increase the context of the language model very, very harshly. And the other issue is that there is still no semantic information contained into the count. So the example here that people give is that vehicle versus cars. Of course, in many sentences in which you encounter the word car, it could be substituted by the word vehicle because they are almost exact synonyms, right? But car is used in daily language, and vehicle, for example, is used in insurance documents. Okay, so when we go and we try to estimate the probability of one word following the other, should we take into account these relative frequencies when we are dealing with this type of semantic information? And the answer is, of course, yes, because this will allow us to harvest more semantic understanding when producing the language model. But of course, this introduces a certain this introduces a complexity we cannot be handled explicitly, right? We would like to automate this process of understanding the semantic content of a language. Okay, very good, very good. So since this is a deep learning class, and whenever you have a problem in life, you try to solve it with a deep learning network, with a deep neural network first. We can try to do the same. Okay, we don't want to deal with English character, ASCII characters. That's too messy. That's not an efficient way of representing a computer. So what we do is that we say, oh, instead of representing a word in an ASCII file, let's just associate a vector to a word. Very good. So we choose the vector to be large enough so that we can represent all the possible English words that we want. Let's say, for example, a vector 20. But not only that, we want to represent it with a vector so we can imagine it as a point in space, and then we can start using geometry over this object. Okay? So the idea of representing sort of these unique entities, right, these qualitative entities into a space is to learn how to use them as vector in a space, right? So to have a certain idea of geometry that we want to impose over how this vector is handled. Okay, very good. So let's say here that we go very large, right? So we have a vector of size 20, but we say that each point in the vector is a floating scalar, right? So that what we want to impose over this space is that if two words are semantically similar, then the distance between the two vectors is small. Of course, this is a very desirable property because then we move the semantic similarity across words into a vector space. So we make the semantic similarity into an object that can be measured by a computer very efficiently. So beautiful idea. But this is how do we understand the semantic context of this, right? So of course we assume that somebody did this job for us, and they came out with some model, and they used a huge corpus of text in which Wikipedia is only 0.001% of the text being considered. and they spend a few $1 million to do this training, and they spend a few months to do the training and collecting the data, so that then we can have a neural network where we take a word, we put it into the neural network. Neural network spits out a vector of size 20, and the vector is such that if we take the embedding for king, we subtract the embedding for man, we add the embedding for woman, we magically observe the embedding for queen. Okay, so of course, semantically, right? This is what we will expect from a space that understands human semantic, right? So this type of embeddings are actually achievable by modern neural network. So famously, there is this word2vec, which was presented in Europe, maybe already 10 years ago, right? And really, people figured out the correct architecture in which you can train neural networks and obtain these properties of the embedding as an emerging property of the embedding. Okay, good. Now that we heard this representation of words as vectors, then now everything becomes easier for us, because we can treat these probabilities as probability over a vector space, which is something that we know how to do efficiently. So now we have we have a conditional distribution that we want to model, and we want to say what is the probability of the next word given the previous word, and this all operates over some sort of uniform representation using the vector space. Good. Then if we want to do this, we already discussed how to do this, and we've seen different network architectures, and the first thing that we want to try is to just do a very simple feed-forward neural network. Okay, so we take all our corpora of the English language, we consider an input sequence of 3 words, and then we teach the network to produce the embedding of the next word, and we just go through all our English corpora, and then we let the network learn this. Very beautiful, very easy. Of course, it's a very difficult task, but if we have enough data, we can imagine that the word will be able to do this. So what we do is this: we take our input X to be the concatenated number of word embeddings that we have, and we take a couple of output layers, and then a couple of hidden layers, and then as the output, we take the softmax of whatever input to the softmax was there, and then we train this for let's say some L2 distance, right, between the output and the true output and the predicted output, and we just let the network learn what is, and then we loop this through all our English corpora, and we see what the network is learning. Okay. So what is the strength of this? The strength of this is that there is no sparsity, right? So however we train this object, this large object is gonna learn from the existing data set that we have. So we're not dealing with having to represent all possible sets of inputs, right? So if an input of 3 words is not present in the corpora of text that we use, the network would have never seen it, but neural networks, they smoothly interpolate between seen and unseen points, and so it will just spit out an embedding and we just live with it. But what is the issue? So the fixed window size is problematic for us, right? Because if we want to increase the number of words that we put into the model, right, then we have to train another model from scratch. There is no flexibility in being able to take sentences of different lengths, which are actually something very common for us to be concerned with. As you increase the window size in order to deal with longer sequences, then the complexity of the network grows very, very quickly, because you're adding inputs, and as you add an input, then you also add parameters to all the hidden layers, and so the complexity of the network scales very, very quickly. We still don't understand word position, right? There is no natural ways of handling word position, so that we don't have an idea of sequentiality as we did in RNN of which words come first. There is no concept of time, right? So we don't have a concept of how the flow of the sentence is producing a logical output. And then the other big thing is that even if the sentence is short, then if our context is very long, we will still have to fill in all the context in order to get one output word, right? So it's very costly to do inference from the network, as we want to make the context longer and longer. Okay, good. So what do we do next? We turn to the network that we love the most in order to do sequence prediction, which are RNN and LSTMs. And the idea is now we're going to have a hidden state. And as the text flows in input, right, the hidden layer is going to build this context, it's going to memorize, it's going to pass the semantic meaning along as the network flows through the English text. And then this is our presentation that we have, right? So we have a word in input. This contributes to the input layer, and then we will have the predicted next word in output. Then this word in output is gonna be verified, right, with the next word in the context, and so on and so forth. And while we imagine the layer to be folded out when we're doing when we're discussing the network in training, then during inference we know that this is going to have a very small complexity because it's a sequential model, right? So the sentence will be presented to the input, the hidden layer will overwrite over itself, and this will be there will be a prediction of the next word, and this prediction can be taken into account in order to modify the hidden layer as it occurs. In the training process, we will have, for example, cross entropy loss, right? So there is the true predicted word versus the true word versus the predicted word. We can take the cross entropy loss. We can propagate this throughout the whole sentence, and we saw how to do this, right? And we see that when we want to train this object, then the total loss will be the average loss across the time steps. And last time we discussed how backpropagation will work across this unfolded RNN. We discussed that as the sentence gets longer, then we have to backpropagate over a larger unfolded RNN. This means that we have issues with vanishing gradients. The chain rule will introduce gradient instability as the sentence becomes longer, and this is something that we discussed last time, and you guys are going to see in the next challenge, in challenge 3. Okay, very good. But this is all good, right? I mean, we know we discussed how to do this last time. While we understand the difficulty of this, we also understand how this is performed, right? So we have the idea that after the sentence is done, the backpropagation chain will start being unfolded. So we backpropagate out to the hidden state. We update the hidden state. We update the hidden state, and then once we have computed the gradient updates, we average all the gradient updates for all the different modules, and then we average them out. So backpropagating through time, as we said, is an expensive process, and instead of doing this for every point in time, and for the whole length of the sequence, what we can do is that we can fix a window size t as the context of the language model, and this is reminding of the window in the n-grams, right? The number of words in our context, and then we will run backpropagation over this window of time t, and we will update the RNN weights by updating the gradients computed over these windows of t, and then we will proceed through a corpora of text. Very good. So usually people want to know what happens when, how do we deal with different length of sentences. Usually we have a symbol which is the end of sentence symbol, and this symbol tells us when the sentence is over. And you can imagine that once the network starts generating the end of sequence, then it will keep generating this end of sequence forever in time, right? So this is like absorbing state in a Markov chain, right? So you generate the sentence, and when you add the end of sentence, then you generate a end of sequence symbol. Good. So we also need a special symbol for starting, so that we know that a new sentence is started. And so you start from a start, and then you predict the language, and you generate the sentence according to the RNN output. Very nice, very natural. And this is actually what was done many years ago or already maybe 15 years ago for generating Harry Potter text, right? So since Harry Potter books are long enough to train a deep neural model, then people built this sort of historical first use of language models that will generate Harry Potter text. So you will be asked, let's say, to prompt a first sentence or a first few words, and then the model will start generating Harry Potter sounding names, Harry Potter sounding text from the prompt that you gave. And probably none of you has read Harry Potter. Already in my generation, it was a book for kids. So I'm not sure. Yeah, not sure if this resonates with you guys. And another one will be for recipes, right? So you can start putting the ingredient and then see which recipe comes out when you put the ingredients in. Very nice, very fun game. So what is the strength of RNNs and what are the issues of RNNs? So the strength is that it can handle infinite length of text. Okay, so we're not concerned by a single window. We can go and look at the amount of memory that we wish. Then the semantics are embedded into the memory. So the hidden layer of the RNN preserves the semantic dependency from text that was seen a long time ago in the sequence. And then you can use the weights for all inputs, so the output is never too funky. And the issue is that it's very expensive to train because, as we said, we have to choose a window T and we have to run back propagation and then slide the window T throughout all the sentences that we have. So a lot of windows to do, a lot of back propagation to perform. We want the windows to be long so we can capture long dependencies in the semantics, but as this goes on, then the back propagation chain gets longer. So an issue. We have to deal with vanishing excluding gradients, right? Because we know that networks train well when we are close to this regime, but this regime is hard to tune, right? It's a lot of hyperparameter to be fixed. And it's easy to lose context. So remember the vanishing gradients that occurs because as the window T over which we compute backpropagation increases, then we are doing more and more multiplication in our backpropagation chain that comes from the change of variable in the derivation rule, in the rule of derivatives. So we saw that the way to obviate the fact that the context keeps piling up semantics in RNN is by using LSTM. So we can add this sort of command gated that tells us when it is necessary to renew the context. And and then we will proceed as this occurs. Okay. So remember these three paradigms that we see so far. One is the n-grams, where we just use the count of the sequence. Then here we have forward neural networks, which are nice, but the window size is limited. And then we have RNNs, and we have a sequential network, which is harder to train. It is slow. And then we want to move to LSTMs. I think, guys, yeah, so we already saw LSTMs a little bit. I think we keep this for next time, okay? I don't want to stretch too much. Let's just keep, just enjoy ourselves. A nice movie review. And so next time we start over from LSTMs. And yeah, and remember that next time you already have the presentation of challenge 3, right? That I posted last week. Okay. So let's see if you guys, let's do the movie review now, and then if you want me to present briefly the challenge, we do it after the movie review. So if you want to read the challenge by yourselves, then you don't need to stay. Okay, go ahead, movie review, please.
Okay, I'll share my screen.
Very good, very good. I should give extra points for movie reviews, guys. Of course, we're gonna do this.
Okay. 1, 2,
Well, you're ready, yeah?
so Today the movie review is the classic gangster movie, The Godfather, and it has 3 episodes, and I'll briefly introduce like what the 3 movies is about, and then I'll talk about my opinion about the movie and what I like and I don't like about the movie. Okay. So the the first part of the movie is released in 1972, and it basically is the talk about the rise of Michael, which is the main male character in this movie, and Don Vito Corleone is his dad, and he was originally a American soldier, but then he uh becomes the head of like mafia, and the first movie is talk about his how he transformed into from like a good man becoming a mafia. And so here is the introduction about the movie. And next slide is the picture. Like here is his originally was like a soldier, and then he becomes the head of the gangster. Okay, so the second episode of the Godfather is released in 1974, and it used uh it used a dual narrative to talks about to illustrate the movie. And one line is about the young Vito Corleone, which is Michael's father, how he rise as uh how he rise in America. And the present line is the how Michael expand the family business to Las Vegas, and while facing the Senate investigation. And the conflict is the Michael survives an assassination at home, and he tries to identify the traitor in within his family, and uh, he found that his brother Fredo was the was the one who betrayed his family and lead to the irreparable fracturing of the Corleone family. And I think the second episode of this of the Godfather really shows the difference between the old Godfather and the younger Godfather. Like the old Godfather always really cares about the family, and I don't think that when he faced some like betrayers in his family, he will like just kill them. Yes. And at the end of this movie is like Michael sits by the lake, and he was becoming very lonely, and his uh children and his wife leave with Michael. Yes. And here is the poster of the part 2 of the Godfather, and here is the Michael now, and here is the young Don Corleone. And here is just the picture like Michael was about to kill the Fredo, and just before he kills him, they are still like uh looking good. Okay, and the part three of Godfather is released after like almost 20 years. So in releasing 1990, and this one like is my least. I like the part 3 least, so that everyone can just like go through the introduction, and the end is like Michael dies alone in Sicily and just haunted by the memories of the female he loved at the end of he has caused. Okay, so next I'll talk about what I like about the movie, and first is the compelling narrative. Like the first one is the mafia perspective, a rare immersive look into the world. Like we as a person in Taiwan, we rarely have any knowledge about the knowledge about the mafia, and it have some historical roots, like woven with the post World War II American history. And there is also like some iconic wisdom I like about the old Godfather said that here is the two quotes from the movie. And the lastly I like most about the movie is audio visual mystery. And here is the brief review, and we can just use the clip to show. This here is my favorite clip about the Godfather, and this is from the first movie, The Godfather 1, and it's at the end, like after the old Godfather's funeral, Michael kills the head of the another 5 families. So we can see. Shows his sister's children.
Exia Deo, e munde Spiritus
the same time he was
Spiritui
going
Sancto
to
Paraclito.
assassinate other
Oremus,
families.
Regis Nostus, per Christum Domine nostrum. Amen. Michael, Crucis Domine in impressiones signatum, od magnitudines gloria tua rudimenta servans, per custodia mandatorum tuorum, ab Domine nostri Iesu Christi, qui Dei regenerabit ex aquae Spiritus Sancto. Qui de te vitivi remission omnia peccatorum, isi te lineat Chrisma te salutis, in eodum Christo Iesu Domine nostrum, in vitam aeternam. Amen. Ego te linea oleo salutis in Christo Iesu Domine nostrum, rabias vitam aeternam. Amen. Credes in Spiritum Sanctum, Sanctam Ecclesiam Catholicam, Sanctorum Communionem Remissionem Peccatorum, Carnes Resurrectionem et Vitam Aeternam. Credo. Exorcisse te mundi Spiritus in nomine Patris, et Filii, et Spiritus Sancti. Urexias et recedes ab hoc famulum Dei Michaeli, isierim tibi impere maledictit damnata. Efrata quores ad aperire, in donum suavitatis, tuatum effulgar diabli apocunquabit eum judicium Dei. Michael, do you believe in God, the Father Almighty, creator of heaven and earth?
I do.
Do you believe in Jesus Christ, his only Son, our Lord?
I do.
Do you believe in the Holy Ghost, the Holy Catholic Church?
I do.
Pater nostri qui es in caelis, sanctificetur nomen tuum, adveniat regnum tuum, fiat voluntas tua sicut in cielo et in terra. Panem nostrum quotidianum da nobis hodie, et dimitte nobis debita nostrum, sicut in nos dimitibus debitoribus nostris, et ne nos inducas in tentationem, sed libera nos a malo. Amen. Michael, ingredere in templum Dei, ut habeas patem cum Christo in vitam aeternam. Amen. Credo in Deo Pater omnipotent, Creatorem Caeli et terrae, et in Iesum Christum Filii eius unigenitum Dominum nostrum, qui conceptus est Spiritus Sancto, natus ex Maria Virgin, passus sub Pontius Pilatus, crucifixus mortus et sepultus, descendere ad inferos, tertia die resurrexere ad mortis, ascendere ad caelos, sedere ad extra Dei Patris omnipotente, inde venturis est judicare vivos et mortus. Credo in Spiritus Sancto, Sanctam Ecclesiam Catholicam, Sanctorum Communionem, Remissionem Peccatorum, Canus Resurrectionem, Vitam Aeternam. Amen. Michael Francis, Ritzi, do you renounce Satan?
I
works.
I do renounce them.
And all his pomps.
I do renounce them.
Michael Rizzi, will you be baptized?
I will.
In nomine Patris, et Filii, et Spiritus Sancti. Michael Rizzi, go in peace, and may the Lord be with you. Amen.
Okay, so yeah, like just after all the assassination, he becomes the leader of the like all the gangsters in the okay. So this clips use the parallel action, which I have seen in many other movies also, and the contrast the nature of the ceremony versus the violence that carry out of assassination. And this clips also symbolize that Michael becomes the ultimate godfather of his spiritual and the criminal families. And that's what is the why I don't like about the movie. And first one is the nameless figures, because Michael's mother is the prime example. Like, she has no real agency and is barely addressed by name. And like, I don't think the all three movies has come out with has mentioned his mother's name. And the next point is the toxic power dynamics. Since Michael's violent reaction to case abortion reveals his obsession with legacy over love. And the transformation, like the domestic violence, marks Michael's final descent from a protector to a tyrant. And this one, this thing is what I see from the movie. Like, once Kate, Michael's Michael his wife told him that it was not a miscarriage but an abortion. Like, Michael just punched her through her face. And this is I think it's my least like of this film, and what I don't like about the movie. And here is my movie presentation, and thanks to everyone.
Yeah, you guys, if you have any questions. Huh? Yeah, the relationship with his wife is also the cultural difference, right? I think the movie stresses that she's American, but he's Italian, right? So there's also this conflict between the two cultures, like how he lives, like he's not real American, right? He doesn't embrace the American culture. And also this thing about between being God, you have this thing about the conflict between like the God and the violence, right? It's also in the way in which in the clip you change from high point of view of the camera and very low point of view. So when you have the shot of the stairs, it's as if God is looking down on the people, right? So when you look from below to above, because you are a low life. Also the choice of the angles, I think it stresses that point.
Yes.
Okay, very good, very good. We should do a Taiwanese version of the Godfather, We should do Gong. That's how we call it.
Gangster movies in Taiwan.
Exactly.
But I don't think is this. that good of like The Godfather. Yes.
I know. We should be like a TSMC employee that try to. Yeah, I think we should do a modern version of criminality. Okay, very good. Thank you so much. So, guys, I'll just take a few minutes to go through the challenge in case you want to hear me talk about the challenge. Of course, if you want to drop off, you let me know. I mean, if you want to drop off, just drop off. I just want to show you the challenge a little bit in case you didn't have time to read it yet, which I'm sure all of you did because you guys are all very good students. Oh, let's thank the student that did the presentation, of course. Very thankful. Yeah? And if you want to present some movie for some extra points, just let me know and we make space for your presentation for sure. So, most important thing, we take this data set, which is the human posture recognition. It's a very nice data set. And then just make sure that you load the data set. Make sure that you segment it because they're very long recordings, so you have to segment it. And then you have a certain prediction horizon, so you have a certain window of which you have to do the prediction. And which prediction you have to do, right? So the Y label of the data set are, I don't remember exactly, but it's like walking, resting, standing up. There are like 6 basic activities, okay? And there are transitions in postures. So you have these as activity labels. So you have the IMU recordings, the recording of the accelerometers, and you have different corresponding activities. And the goal of the challenge is to have a sequential model that does the prediction of the activity based on the recordings, okay? So try to use GRUs, LSTM, temporal convolutional networks, of course, a new model that you have to play with, and try to do the prediction. Try to vary the sampling time, the sampling frequency, the sampling windows. Try to subsample the data and see how the prediction goes. Then now try to derive embeddings. Okay, as we saw in the presentation today, embeddings are very, very important. So the idea is that if you take raw data, you can have some sort of pre-processing of raw data into a vector representation that you can use as for downstream tasks. So remember also challenge 1 or challenge 2, you were doing this contrastive learning in order to create embeddings for MNIST. So this is also something that you can try to train, right? You can take 2 pieces of activities across different people, and you can try to align them using contrastive learning in order to produce embeddings. And then when you want to work with the sequence, you don't work with the measurement directly, but you create an embedding and you work with the embeddings, okay? In the embedding, you can learn how to compress the data, how to represent the data in a very compact way, and that's something very valuable to learn. And then you do the activity detection as a quickest detection. So now you do a network that looks at the embeddings and then produces an activity label only when the network is sure that an activity is taking place. So this is where you use the RNN sort of start and stop command in the RNN. And then the last task, which is always the trickiest one, is personalization, right? So people have different height, different lengths of the limbs, different ways of moving, right? So you can imagine that if you have a model, right, you can have a generic model and then have a single signal, right, for a certain individual that you use to modulate the output of the model. And this is called one-shot model personalization. So the last topic of the challenge is this one. Okay, very good. Guys, this is one of the few times in which we have really run almost the entire length of the class. So let me know if you have any questions. Otherwise, I'll let you guys go. And next time you do the presentation, probably we do the same thing as last time. We do 3 groups, one week and the other 2 groups the next week, since I like to listen to you guys instead of talking. Let me know if you have any questions about the challenge. If you have any comments, leave them in the comments on the overleaf. I will follow up with it. Thank you again for the movie presentation. If you want to present next time, let me know. We say hi to the people on YouTube that are gonna for sure listen to this video and leave a like and subscribe. And I'll see you guys next week. Okay, ciao guys. Stopping the recording now. Ciao ciao.